let's go through. So on Friday, last week we did a thermodynamics review. We looked at why we need a undercooling to have enough driving force for nucleation. But what happens if you don't have sufficient undercooling, you're in a nucleation limited regime, so you'll have easy growth. If you're too low, you won't have atomic mobility, so you'll have a ton of nuclei, but you won't have enough diffusion for the particles to grow to any meaningful size. And we talked about the formation of GP zones, how essentially they're clusters of atoms. I had an interesting question that was someone asked to Ben, and I thought I'd pick it up real fast, because it was someone asked why do the GP zones form at all? Why do the clusters form? Right? And you have to remember, you're quenching down from this single phase region, right? And when you cool down, you're supersaturated in copper, right? So you want to phase separate, right? Thermodynamically, you want to nucleate theta, but that's too difficult because it's too big of a unit cell, lattice mismatch, big incoherent interface with a high energy, right? So if you look on our curves, where's our our free energy curves here, right? By forming the clusters, we're able to reduce the copper, right? Remember, our solution wants to separate. The copper wants to be with other copper, and our alpha matrix wants to be drastically reduced in copper, right? So by forming these clusters of copper atoms, we reduce the composition of our alpha matrix, and we reduce over here. This is our volume, our free energy drop, the volumetric free energy to be specific, right? And so, that's sort of what you want to keep in mind. It's not immediately obvious if you just think about it why copper atoms want to be together. It's not so much that the copper atoms want to be together, it's that thermodynamically this solution wants to phase separate. Right? It's not a stable solid solution anymore at the lower temperature. We looked at other phases. We looked at the theta double prime, the theta prime, and the theta phase, and looked at how the composition changes as we nucleate the phases, and how heterogeneously nucleating the other phases from GP zones in the previous phases is much easier than nucleating the thermodynamically stable theta phase, right? And this is all in aluminum copper, but as we get to describe other alloy systems today, and then when we do at the end of aluminum, when we look at all the commercially important alloy systems, we'll see that we have GP zones in aluminum magnesium. We have GP zones in aluminum silicon, right? And they have different morphologies and different equilibrium phases, but it's a general theme that we'll see over and over again through different aluminum alloys. So on Friday, I left with a teaser, right? And I'm sure everyone was thinking really long and hard over the weekend, right? I mean, they were excited to come in today and learn the answer to the question of what on earth vacancies have to do with the nucleation rate and ease of nucleation of GP zones and other secondary phase particles, right? So any Anyone want to throw out an answer? Someone have a burning desire and spent all weekend reading up? Anyone just not care? So how do we get clusters of copper atoms? What has to happen? Diffusion, right? We said it's short-range diffusion, but it's still diffusion. How do atoms move? How do atoms diffuse? They jump. What do they need? What do you need to make a jump? Vacancies, right? You can't jump, right? The probability of just two atoms switching places, right, is pretty low, right? So what you need is a vacancy there for one atom to jump into, right, and leave behind it a vacancy where it was. So does it make sense that the more vacancies you have, the easier diffusion is going to be, and the easier your phase transformation is going to be, right? So this is some data from aluminum silicon, right? And recognize the name here, right? There's this guy Turnbull. Really famous metallurgist. He did a lot of the work on nucleation and growth, the fundamental theory, right? He did very controlled, very detailed first solidification experiments, but really one of the important metallurgists of the 20th century. So if we look at some of his, the classic work that they did, and we look at an aluminum silicon, so slightly different alloy, but let's quench from two different temperatures. So first we're going to we're both in the alpha field, right? So we're all a single phase FCC, stable solid solution of aluminum and silicon. And then we'll quench from the near the solidus line, right? Remember, this is called the solidus line because it's solid on this side and alpha plus liquid on this side. And then here we'll quench from just north of the solvus, right? And we quench down to room temperature. And if we look at this low temperature, we have about 1 million precipitates per cubic centimeter, right? And they've nucleated heterogeneously, right? If they've nucleated heterogeneously, where does that most likely mean that they nucleated? We're going from a single phase solid solution down. Grain boundaries, right? So if we quench from near the solvus down, we get a lot of precipitates at grain boundaries, maybe some at dislocations, Frank loops and other type things, but primarily on grain boundaries. If we quench from the higher temperature, we have 9 orders of magnitude, 10 to the 15 precipitates per cubic centimeter, right? And we have homogeneous nucleation, meaning we're nucleating uniformly throughout the bulk of our sample, right? So what's controlling this? Well, obviously vacancies, right? I wouldn't have had this on the slide that says role of vacancies otherwise, right? But why are the vacancy concentrations so different in these two cases? You have more vacancies, but why do you have more vacancies at higher temperatures? Right? So that's what it shows here. right? Vacancy concentration is a strong function of temperature. So why is that? Well, we need to think about our different types of crystal defects, right? Point defects, vacancies, interstitials, line defects, dislocations, planar defects, right? Stacking fault twins, grain boundary, and volume defects, voids, and bubble and gas pockets or things like that, right? So think about all these other defects. If we heat up our sample, do we get more dislocations? Right? Or grain boundaries. Do our grains get smaller when we heat up our sample? Right? Why are vacancies different? Vacancies have a thermodynamic equilibrium concentration. Right? You've probably heard that before. You may have done the calculation. Right? It's not that hard to do. In fact, we'll take a quick look at it. But where do vacancies come from? Right? Or equivalently, where do the atoms go when you make a vacancy? Right? How is a vacancy formed? Right? There's something called a Frankel defect. Right? You probably heard that term more in terms of ceramics than metals, but they still exist in metals. What is that? Right? It's when an atom jumps into an interstitial space, leaving behind a vacancy. Right? In a close packed metal, how likely is that? Right? Vanishingly small, we'll say. So we can just ignore that effect for the overall vacancy concentration. Right? But where can we make a vacancy pretty easily? Right? Any of our planar defects. Right? A surface. Right? We have a surface of a perfect crystal. We have a surface of atoms. One atom can hop essentially up and leave a whole vacancy, and then which then can diffuse down into our sample, moving our free surface up this way as it happens. New atoms hop from one layer to the next. Grain boundaries work the same way. We already said grain boundaries are these beautiful regions of open space in our crystal, right? So essentially, it's not hard for an atom to jump onto a new position on the grain boundary, creating an empty spot, and that vacancy can then diffuse in. Edge dislocations. How do edge dislocations create vacancy? Climb, right? Edge vacancies can't cross-slip, right? The only way they can move from one plane to the other is to climb. Depending on whether you have positive climb or negative climb, you're going to create or destroy a vacancy. Right? So these essentially all act as vacancy sources and sinks. Right? Okay. So the energy to form a vacancy isn't super large. Right? 0.7 eV. What's an electron volt in joules? What did you say? Yep, 1 times 10 to the power 19, right? For calculations, the extra little bit doesn't matter. So, right. Think of order of magnitude. So 10 to the minus 19 joules, right? So what's a joule? Right? A joule is not a particularly large unit of energy either, right? Right? It's the amount of heat dissipated by 1 amp through a 1 ohm resistor in a second, right? So it's like the amount of heat that comes off a 60-watt light bulb every second. Right? Not a whole lot. The amount of work you do by a 1 Newton force acting along a distance of a meter. A Newton is super light. right? So it's not, and we're going to be at around 10 to the minus 19th joules, so really small activation energies to create a vacancy, right? All you have to do is overcome a small energy barrier to move from one site to the other. Okay? So if we want to think about the equilibrium vacancy concentration, right, our enthalpy is just going to be that 0.7 times the number of vacancies that we form, right? That's monotonically increasing. But we have to think about the other contribution to the Gibbs free energy, the entropy term. If we go from a pure crystal and we introduce vacancies, what does that do to our entropy? How many configurations do we have for a perfect crystal with no point defects? One possible configuration, right? If we introduce a vacancy, a single vacancy in a mole of aluminum, how many different configurations do we have? 10 to the 23rd, right? We introduce, right? You see how rapidly the entropy term grows, right? It's the natural log of the number of configurations, right? Is going to be our entropy. So it goes down like this, but of course it's a natural log. So the more and more the incremental increase in the entropy with each new vacancy gets slightly smaller. So eventually our enthalpy term is going to win out in the long run, but our entropy term wins out in the short run. So that means we have a minima, right? A free energy minima that gets larger and larger as we increase the temperature, right? As we increase this T, our temperature, this term gets more negative, so our minima gets deeper and it shifts to the right, right? More and more equilibrium vacancies, right? So schematically we can see how that works, right? Right, and which is why point defects have an equilibrium concentration, because the enthalpy term to form them is quite low. The energy to form a dislocation is quite high, right? So the entropy penalty can never win out, or the entropy boost can never win out because it costs so much to create one, right? So on the next two slides, I don't expect anyone to learn this or memorize it, but it's worthwhile seeing it once, right? And I'm sure you probably did this before at some point in time, is calculate the equilibrium number of vacancies in a crystal for a given temperature, right? So in the undergrads, how many people have done this calculation before? You're a grad student. But you did it in your undergrad. I did it in my undergrad, right? This was like a thermodynamics homework question, right? So what I did is I added a small term that's not in Gaskell. This is the vibrational entropy term, right? Because, right, what is this? What is the vibrational entropy, right? If you all of a sudden put a hole, right, if you have a bunch of atoms and they're all vibrating on a lattice and you take one out, it's going to affect the vibrational structure, right? You can think of a bunch of harmonic oscillators, right, all connected, a bunch of springs all connected, and it makes sense that if you vibrate that, it's going to vibrate differently if you're missing one of those connections than if you have them all there. So there's a vibrational component to the entropy. And it's not hard to work through. So I have all the calculations are all here. It's pretty easy to do. So this is the number of configurations. This is just combinatorics, right? This is basic statistics. So the entropy is, of course, Boltzmann constant times the natural log of this. This is the configurational entropy term. So we have the Gibbs free energy. How do we find the minima of Gibbs free energy? Right? Calc 2, we take the derivative of it, right? And look for the critical points of our function. So we take the derivative and set it to equal to 0. And then we have this, and then we have to use, remember, I know for a fact you use Stirling's approximation when doing entropy calculations before. It's a way of calculating the natural log of a factorial, because you can't just plug that into your calculator. So it's really, really, really large, right? Think if you have a mole of atoms, what's 10 to the 23rd factorial, right? Much larger than any computer can handle, right? And then from there, it's just a little calculus to work through, and you get an expression that looks like this, right? It's the number of equilibrium vacancies for a given number of atoms that you have, right? So everyone should sort of work through it once, right? And you can see the result here. And even with the vibrational term, it still looks a heck of a lot like it did without, right? That vibrational term ends up being small. But it's natural to ask whether or not it's important, right? It's just a correction on this linear term. It's just going to slightly reduce the slope, right? So that means you're going to have if the slope is reduced, you're going to have a slightly higher number of vacancies, because if you include the vibrational term, right? So it's kind of an important concept, right? That point defects are going to have a equilibrium concentration, whereas dislocations and grain boundaries are not, right? And this is super important for the welding guys too, right? If you want to think about transport in a heat-affected zone, right? Vacancy-mediated diffusion is really, really, really critical. So how do vacancies influence nucleation, right? So on quenching from a high temperature, we're still going to have a supersaturation of vacancies, right? Where can they be annihilated, right? The vacancies have to move to sinks. We can't just, if we have a hole in our lattice, a missing atom, we can't just magically populate an atom there. That vacancy needs to diffuse to a grain boundary or a surface, right? Or an edge dislocation for Klein, right? It can't just disappear, right? So there's a time dependence here. So if we quench from a high temperature, rapid cooling, we have a significant amount of supersaturation that occurs. This can assist in local diffusion, and it can also reduce the strain fields around atoms, right? Which is going to be reducing the activation energy for the formation of GP zones. If our substitutional atom is larger than our aluminum matrix for silicon or germanium, right, a large number of vacancies reduces the strain of making a cluster of silicon atoms. All right. So what's the magnitude of this supersaturation? All right. So we age an alloy for 900 seconds, so 15 minutes at 130 C, right, after the quench, right? You can do a calculation and find that the mean distance between GP zones is 10 nanometers, right? So square root dt, right, gives us a diffusivity of 10 to the minus 16. Right? Is that fast or slow? If we look up the thermodynamics, the data on the table, right, and we just look up the diffusion data for copper and aluminum, it gives us a diffusivity of 10 to the minus 18, right, centimeters squared per second. Right? So it's roughly 2 orders of magnitude improvement in the diffusivity, all because of this supersaturation of vacancies, right? So in aluminum copper alloys, GP zones can form when we age them at room temperature, right? This would be completely impossible without a very large vacancy concentration, right? We would need to age at elevated temperatures to get significant diffusion, which puts us close to or above the GP zone solvus temperature, right? Okay. So in general, we need a critical supersaturation of vacancies for the nucleation of GP zones, no matter what our aluminum alloy is. If it's an alloy that is heat treatable and forms secondary phases, right? Right. And the aging temperature, the amount of this supersaturation that we need is going to be dependent on the aging temperature, right? So the difference is, right, if we age at 190, I gotta be careful about how I say this. If we raise the temperature up, right? So this is at 130, right? You look on the table and we said our diffusivity is 10 to the minus 18, but with the vacancies, we get an effective diffusivity of 10 to the minus 16. If we raise our aging temperature up to 190 C, our diffusivity, our equilibrium diffusivity data off the table is 10 to the minus 16, right? So our we've essentially caught up, right? We raise the aging temperature up 60 degrees, and our diffusivity has caught up due to the temperature change, right? So we've got our two orders of magnitude back. So the GP zones would be slightly larger in scale, a little more well separated, right? So our vacancies still help, but the amount of vacancies, critical supersaturation of vacancies that we need at 190 is significantly lower than that we needed at 130, right? Yeah.
So diffusion at 190 is higher.
Yeah.
So
right. So at 130, our diffusivity of copper and aluminum is 10 to the minus 18. But if we have a lot of vacancies, we can boost this up to 10 to the minus 16. Right? But at 190, we're already at that 10 to the minus 16. Just a factor of 2 relative. Right? So we're still we have easier diffusivity here. Right? So the aging temperature comes into play a lot. Right? And the strain term, if we look at the effect of this, right, our strain term is going to pull this line here, meaning that our activation energy for nucleation is going to shrink and our R star is going to get smaller, right, because we can accommodate some of the elastic distortion with the presence of additional vacancies. Right. Okay. So when we look at the microstructure of these, Right? So we see that we get our fine dispersion of precipitates that we want, but if we approach a grain boundary, we have a region that's essentially parallel with the grain boundary that are denuded of precipitates. Right? We don't have any strengthening secondary phases right near the grain boundary. Right? And so these are precipitate-free zones. Right? And anyone have any idea one reason they can form? There's two common reasons why these would form. But being that we were talking about vacancies, what's a vacancy reason why precipitate-free zones would form? What's the connection between grain boundaries and vacancies? I'll pull this out of here. If I have to pull all your teeth. Grain boundaries or vacancy sinks, right? So we said vacancies need to diffuse to the grain boundaries to be annihilated, right? So does it make sense that we have a lot of vacancies out here, but not so many vacancies here? So the width of this precipitate-free zone is going to be related to what? Right? During the quench, before we quenched, we had vacancies uniformly, right? At the equilibrium concentration. When we quenched, now if we didn't nucleate here, that means we have a vacancy concentration that's below our critical level. Right? So what does that tell us about this width? The width of the precipitate-free zone. That's the zone where vacancies were able to diffuse to this grain boundary during the time of the quench. Right? Okay. So close to, right? So essentially we have a picture that looks like this. Far away from the boundaries, we're at our I said this wrong. It's not during the quench, right? It's during our aging hold, right? Be careful of that. I was getting ahead of myself, right? So basically, at quench, we're going to have a real narrow region where we don't have enough vacancies, right? But essentially, as we age, our vacancies are going to diffuse to the grain boundary, right? So we'll have a vacancy profile that looks like this during aging, right? And the width of the precipitate-free zone is essentially where the critical free critical supersaturated vacancy concentration is. So I was getting ahead of myself here with the quench times, right? We'll see if you have a fast quench versus a slow quench. You have vacancy concentrations that look like this. But over time with aging, you'll see these spread out as vacancies have time to diffuse to the grain boundary. Right? So that's one reason for precipitate-free zones. Anyone think of another? Right? So if we want to form precipitates, we need one to have sufficient solute for the precipitate to form, and we need to have sufficient vacancies for diffusion to occur. Right? Well, we talked about a vacancy mechanism why we'd get a precipitate-free zone? Can you think of a solute mechanism why you'd get a precipitate-free zone? Where do we often see secondary phases in polycrystals? Grain boundaries, right? Why do they form at grain boundaries? Right? It's easier to nucleate, but that wouldn't happen unless certain solutes are attracted, segregate preferentially to the grain boundaries, right? So that's the second reason you can have precipitate-free zones, right? Is that if you have a solute that segregates to the grain boundary, right, it will leave a depleted region near that grain boundary so that the secondary phase can't form there, right? And the profile for solute is not as pronounced as that for the vacancy. So you have sort of as you get in closer, you stay closer to the bulk concentration, then you get a dip, and then often you'll see a precipitate particle on the grain boundary, right? So we have both of these effects. You can see this in aluminum, zinc, magnesium alloys, right? So here's our precipitate-free zone. Here's secondary phase, a secondary phase forming on the grain boundary, right? And then these will grow by Oswald ripening, right? And so as these precipitates grow, what's going to happen to the precipitate-free zone? Precipitate-free zone will grow because you'll have solute diffusing away from the bulk towards the grain boundary, right? And then, so here's the clue for those of you that studied your phase transformations well, right? What's going to happen to the rate of the growth of these particles as that happens? It's going to slow, right? Because it has a farther distance to diffuse, right? So it's going to grow parabolic, right? Square root of time dependence, right? So small amounts of additional elements can really throw a wrench in this whole thing, right? So if we add a little bit of silver to aluminum zinc mag, we completely eliminate the precipitate-free zone, right? Right? So there's a significant reduction that we see in these, right? So if we look at all of the factors, right? So interaction of the solute with vacancies, right? That can reduce the effective vacancy concentration, reduce the rate of nucleation, right? So if we introduce cadmium, indium, and tin into aluminum copper alloys, right, we really arrest or retard GP zone formation because of the interaction with these elements and the vacancies, right? The vacancies are not there to are not able to diffuse because they're so tightly correlated with the alloying elements, right? Trace elements can also raise the GP zone solvus temperature, right? So if we raise the solvus temperature, we are doing what? If we're aging here, we have a larger undercooling, right? Larger undercooling means what with respect to nucleation? Right? Higher driving force for nucleation, Higher driving force for nucleation means we're less dependent on diffusion to bring clusters together, right? So we have a smaller R star, so our precipitate freeze zone is drastically reduced if we can raise our solvus a little bit, right? And then we can also alter the interfacial energy of the equilibrium phases, right? If we can reduce the interfacial energy of the intermediate or equilibrium phase and make those easier to nucleate, either homogeneously or heterogeneously, right? Then we're not necessarily going to form GP zones, and we're not going to form essentially precipitate free zones, right? Or we can form a completely different precipitate, right? So basically, the precipitate free zones around the grain boundaries are really going to be altered pretty dramatically by the trace elements that we alloy with, the specifics of our heat treatment, where we quench from, and what our aging temperature is. Remember, where we quench from gives us the vacancy concentration that we're starting with, right? And then our quench rates. Right? If we quench too slowly or cool too slowly, we eliminate our supersaturation of vacancies, right? And so essentially this just is looking at that aging at 130 versus aging at 190 example that we showed before. And what we can see is that, all right, well, maybe I'll add an additional sort of question to ponder, ask what you guys see here. What are the primary differences here? We see theta prime form a lot earlier, right? After a couple hours instead of after a couple tens of days. So interesting interpreting this graph. It's a good. I like exam questions like these, right? Look at some data and tell me what's happening inside the alloy based on the data that I give you. Right. How are we doing time-wise? Okay, cool. So there's a couple different alloy-dependent aging treatments that we can give these alloys. So the first one is we start from the two-phase region, we quench above the GP zone solvus, and then age above the GP zone solvus. Right? So it should make sense after everything that we talked about that we're not going to get a fine dispersion of secondary phase particles that are good for strengthening at this. What are we going to get? Right? If we're quenching and aging above the GP solvus temperature, we're going to get what types of particles are going to form, where are they going to form, how are they going to nucleate. if we're above the GP zone solvus temperature, we're never going to nucleate those, right? So what phase are we going to nucleate? We're going to intermediate phases, right? So theta prime in this, if we're talking about aluminum copper, theta prime is, the solvus is pretty close to the GP zone solvus, right? So chances are we would nucleate theta double prime in copper, right? But theta double prime was semi-coherent at best, right? Largely had some large facets that were incoherent and a large spacing, so we would have to nucleate those heterogeneously. If we nucleate heterogeneously, do we have a lot of strengthening effect, right? If nucleation is hard, but we're at a high temperature and growth is easy, we get widely separated big particles.
So right. Previous thing that you said, when we have more vacancy, so we have more diffusion. But when we have more diffusion, we may got bigger particles.
So it's all a matter of temperature, right? If we're down here, we don't have, if we're low, say 130, we don't have nearly enough mobility, right? But we have a large driving force for nucleation. So we can nucleate the dispersion, and they'll be nucleated out small. If we're up here, well above the solvus, we're at a higher temperature, right? Remember, diffusivity is Arrhenius, right? So it's exponential with.
So if we.
But here we're above the solvus, right? So those GP zones will just never form, right? But we're trying to nucleate phases that are very difficult to, right? So the probability of a nucleus forming is very low. When it does form, it's much easier for things to diffuse to it and it grows than for other nuclei to form, okay? But this is the case with aluminum mag, right? If we have too much magnesium, or we have magnesium 5%, so magnesium 3% is typically what the aluminum magnesium composition is. So our GP zone solvus is below room temperature, right? So at room temperature, even if we held it cryogenically, if we then brought it up to room temperature, all our GP zones would dissolve, right? So this is the case for aluminum mag. If we think about alloys that are quenched below the solvus, and then the aging treatment is above the GP zone solvus, right? We can nucleate some GP zones on the quench, and then when we age, we can nucleate our secondary phases heterogeneously on them and get a finer dispersion. The third case is where we quench and age below the solvus, which is what is used for most age hardening systems, right? Right, but at this low aging temperature, it becomes harder to nucleate our second phase, our intermediate phases. So often we have a duplex treatment. Quench and age at one temperature to nucleate GP zones, and then raise up to a higher temperature to nucleate heterogeneously on the GP zones as the GP zones dissolve. Right? So by doing a duplex kind of treatment, we can get a very refined dispersion of the intermediate precipitate, right? Which is what we want in aluminum copper. Again, in the 2024, the magical aerospace alloy from World War II, right? We want, it's used in a a condition with a very fine dispersion of gamma double prime, of not gamma, theta double prime, right? So quench, nucleate GP zones, raise the temperature. Theta double prime nucleates heterogeneously on the GP zones, which are then consumed and dissolved away. Right? So what makes a good age hardening system? Right? If we want to design an aluminum alloy and we want it to be precipitation strengthened, how do we go about doing that? Right? So the first one I threw on there was Solvis line curvature. What do I mean by Solvis line curvature? Right here. If I don't have a pronounced region where at an elevated temperature I have a solid solution, right? I'm not going to be able to quench and create a large supersaturation, right? If this curve instead, now that I learned how to do this, and right, if this in turn looked like this, right, and this was part of the alpha plus liquid field, the largest concentration that I'd be able to saturate in, right, of my alloying element would be much smaller. So that I would be able to have at the end, I would only be able to have a much smaller number of precipitates, right? So this high degree of Solvis line curvature is really important to be able to create an effective hardening system, right? Homogeneous versus heterogeneous precipitation. If I want effective hardening, I want to nucleate my initial metastable phase homogeneously, so it's uniformly distributed throughout my system, right? I'm hitting these points again and again and again, right? Because it's really important. We want a uniform dispersion of fine precipitates for strengthening. The only way we can do that is by homogeneous nucleation. So we need to have a low barrier, a phase that's easy to grow, right? Right? Because heterogeneous precipitation tends to happen on dislocation and grain boundaries. So that doesn't always translate into, I forgot to bring the attendance sheet. So while I'm thinking about it, can you guys fill that out before the last couple minutes of class, right? Okay. So the last part of this, I want to go through a couple different alloy systems. And just like we did with copper, look at what the different precipitates that form are, right? And the first one of these is aluminum mag. And we can see we do have a reasonably strongly curved Solvis line, right? But our GP zones are spherical in shape. So what does that tell us? That they're spherical in shape rather than plate-like. Why were the GP zones in copper plate-like? Elastic distortion due to the size mismatch, right? And essentially, where did our strengthening in GP zones come from? The elastic interactions between the dislocation and the strain field around the GP zones. So if we have spherical GP zones, right, this likely tells us that our elastic distortions aren't all that great because aluminum and magnesium are much closer in size than aluminum and copper, right? And so we're not going to have nearly as good of strengthening from GP zones. And the solvus is very close to room temperature or below room temperature for the GP zone solvus. Right? So we'll pick this back up Wednesday. I will hopefully get through these alloys. And then on Friday, we only have a very short lecture on, well, it'll probably be one full day Friday, on some solid solution strengthened effects and some microstructure features that arise during processing of aluminum alloys.